determines the outcomes of these alkene reactions. Basically says that the major product or major products in these reactions will be more heavily substituted alkenes. We'll put this into a picture. It'll make more sense in a minute. But major products will be more heavily substituted alkenes. These are more heavily substituted than this one. This is a disubstituted alkene, a disubstituted alkene, a monosubstituted alkene. The distinction means how many non-hydrogens are attached to the alkene. Here are 2, disubstituted. How many, there's 4 things obviously attached, but the way to distinguish it is how many non-hydrogens are attached to the alkene. Here are 1 thing, so this is monosubstituted. So those names come into play in Zaitsev's rule, the full Zaitsev's rule, based on lots of painstaking measurements. Tetrasubstituted alkenes will be more stable or more favored, in these reactions. This is a tetrasubstituted with 4 carbons. This is more stable than a trisubstituted. And in these types of reactions, if we're making both of these, this would be the major product. If we're not making this, then it's not relevant. But in general, this is a stability trend, and that stability trend applies to major products for these types of reactions that you can use to make a prediction. Trisubstituted alkenes are more stable than trans disubstituted. Trans disubstituted are more stable than geminally disubstituted, which are roughly equal to cis disubstituted. So these 2 patterns are both disubstituted. One's geminal, meaning both carbons are attached to the same carbon. This one is cis, we know from the distinction between cis and trans. And those are roughly the same stability. This one is more stable. And then the last one I didn't really have enough space for, but that would be monosubstituted, where we have 3 hydrogens but only 1 carbon. Okay, so this general trend, it's very easy to understand. More heavily substituted alkenes are more stable, and those turn out to be the major products in these types of reactions. So this is a trend that's important for us to put into our notes. That basically summarizes it there. It's not a particularly vexing or challenging trend for us to incorporate or understand. Let's just look at some substrates here, and then we're going to get into our Newman projection work that I want us to do today. We're just going to draw a substrate here. And I'll usually use bromide for the leaving group in all of these reactions. We're just going to react this with sodium methoxide. And I want you to ponder this for a minute to determine what the product of this reaction is, or if something else is at foot. So I want you to find all the beta hydrogens, do an acid-base reaction of those beta hydrogens, and draw any product that you might think is possible. Or for this compound, if maybe you think a reaction is not possible, you should state why definitively. So just spend about 30 seconds on this. Draw beta hydrogens, identify them. If there is beta hydrogen, do an acid-base reaction and draw an alkene. Maybe if you can find a reason why this reaction you think wouldn't work, state that kind of definitively on your paper. When I approach this type of molecule, I just start labeling things alpha. There's only 1 beta carbon here. In the SN2 reaction, in the E2 reaction, there is no chemistry at alpha. Doesn't do an acid-base reaction here. Just would never work. If you did that, there's no way to get the leaving group to leave. There'll be negative charge on carbon. There'll be no double bond. The chemistry actually happens at the beta position. And for this one, at beta, there's no hydrogens. So this doesn't react at alpha to do E2. If you don't have beta hydrogens, then there can't be any chemistry here. So here there's no chemistry possible. And so for this particular example, there's no reaction possible. Okay? Just requires that we always find beta hydrogens. So whenever we set up a problem and we're going to try an E2 reaction with it, identify alpha, identify all beta positions. This one just had one. And then look to see, are there hydrogens attached to this position? If there aren't, reaction stops. Most of the time, there will be hydrogens here, but I just want us to keep this in mind and keep this straight. Let's actually go back one page. We're going to go back in our notes to 2-bromobutane. So we're going to revisit 2-bromobutane. Let's use sodium methoxide again as our base. And now we're going to explain. We're going to explain where cis and trans comes from. So for this particular molecule, now at this particular state of where we are, we could look at it, alpha, beta, beta, beta 1, beta 2, doesn't matter what we call these, it could be called beta 1, beta 2, this is just to keep track of everything you need. Just looking at this molecule, and what we did a few minutes ago, we should be able to predict products here, that double bond forms between alpha and beta, we lose a hydrogen, and we lose a bromine. So, making this particular alkene, we should see the relationship between these two. And we know at the beta 2 position, we can make a double bond between these two. And kind of the way this molecule is drawn, if we had a base pull off one of the acidic protons at beta 2, there's two of them there. Double bond starts forming here, leaving group forms, we could draw this trans alkene. And I'm saying the cis alkene is also possible. Okay? And what I want us to do now is explain where these two things come from a much more high-level discussion. Everything up until this point is critical and essential. These mechanistic steps we worked out, we went through them nice and slowly. I'm just going to put very, very briefly the formation of this 1-butene molecule is in our notes already. We drew it out in an expanded fashion. Base pulls off this proton. This proton's acidic because it's nearby a leaving group, 1 carbon away. Bond starts forming, leaving group leaves, and we get this particular product. And very quickly, when you see these two types of things in your mind, you should also be able to start to rapidly say, oh, we're going to make this alkene. You know, if I ask predict products, not explain the mechanism, you should be able to look at this kind of and have a feeling like, oh, there should be double bond here, double bond here, all right? But what we're going to do now is we're going to take these and explain it. And the way we're going to do this is at the beta 2 position, we're just going to use Newman projections to explain how we get cis and trans here. And this will be an opportunity. I'll actually ask you on your own to predict what we would get. So at the beta 2 position, previously we were interested in expanding these two positions. This is alpha and beta 2. And we know that there's free rotation about this bond. Actually, I'm going to darken in this bond because we're about to draw a Newman projection looking down this bond. Okay. So this is where all the action is taking place. The base is going to attack here. We're going to form a double bond here. Bromide's going to leave. But let's actually look really carefully using Newman projections about this. Let's just take this and quickly draw it into a Newman projection. And the way I want my eyeball to look down this thing is my eyeball here. It's red and bloodshot. I'm going to look down this particular bond and draw a Newman projection and just write what we think we'll see from this. Okay? So we're kind of looking down the carbon 2, carbon 3 bond from the 3 end. It doesn't really matter, but let's just imagine if we're looking at this carbon, what would this molecule look like? And we start a Newman projection. Let's just start a Newman projection, the simplest ones, which are these staggered conformations. And our eyeball is going to be looking here at the 3 carbon. The 2 carbon is kind of obfuscated behind here, and we just have to draw in everything that's attached to it. So when I'm looking at this particular molecule, I see a methyl group up. I'm just going to put the methyl group up. The other 2 things attached are hydrogen and hydrogen. Okay. So this should be pretty straightforward for most of you. And when I took over the class from Dr. Marinas, I definitely reminded you of the significance of all the things you did with him. They're all important. They were all going to come back. I gave you fair warning that if you were weak on those things, you should revisit them right away. And if you didn't, this is going to be challenging. But for the rest of us, we're going to move ahead forward under the assumption or presupposition that you did your part and know this material. The back carbon has bromine, methyl group, hydrogen attached. So you might have drawn something different than this, but this is, with different orientation and location, but this is what you should actually draw. This is what I see. And if you drew things in slightly different orientation, it's no problem because we know that these things rotate completely. Okay? So